So it's a great pleasure to introduce Hugo Duminil-Copin, who'll talk about the existence of an unbounded nodal surface for high-dimensional monochromatic waves and some other things which imply.
Well, thank you very much. Thanks to Peter and Svetlana for inviting me to talk. So I decided to do a talk where I'm not going to spend too much time on the history to be able to tell you a little bit about the proof, because I think that many of you are actually interested in the proof. But let me still remind you a little bit of what we are talking about. So the models at hand are, there are two models. On one side, there is going to be the model that I guess most people are interested in, which is a monochromatic wave. Monochromatic waves. And on the other side, there is going to be another model, the Bargmann Fock model, which will be interesting for us in the framework of understanding monochromatic waves, because in high dimension, they kind of look the same when you project them on a subset. Subspace. Okay, so these are two Gaussian spaces, Gaussian fields, sorry. It's a little bit late and I'm a little bit tired, so I'm going to try to do my best, but sorry for the... So it's both Gaussian processes, and I need to tell you, in order to characterize them, what is their covariance function. So in the case of Bargmann Fock, it's very easy. The expectation of x of x, x of y is simply exponential of -1/2 of the Euclidean norm between x and y. Okay, so this, you just take the Gaussian field with this covariance function. On the side of monochromatic waves, there is also an explicit Gaussian covariance. It's just that it's maybe a little bit tricky to define it directly. So what I'm going to do, I'm going to use a characterization. So the covariance will be just the Fourier transform on the sphere, the d-1 dimensional sphere of e to the I x minus y psi d nu psi, where nu here is just the unit measure on the sphere. Okay, so how measure.
Your Gaussians are all centered at the origin.
Sorry?
Your Gaussians have mean zero. Yeah.
The Gaussian of, Gaussian of mean zero, yeah, of course. Yeah, there's a Gaussian field of mean zero, you're right. Just for people here, it's clear what is the dependency in the distance. So it's something very nice like that. But here, I just want to emphasize one thing, which is that the function itself is radial, but it's not positive, which makes the life of probabilists like me much tougher and also more interesting, because in particular, the field itself will not satisfy the FKG inequality. It will not be positively correlated. But one important thing that one needs to understand, two important things, is first that it kind of decays very fast in x to the minus d-1/2. Okay, so it's still a fairly rapid decay of correlations. And the second thing, which will explain a little bit more why later on we will be able to extract results from the Bargmann Fock side to the monochromatic waves, is that when you project so here, when you look at this guy, you recognize exactly that this is the Fourier transform of a Gaussian measure. And if you look in high dimension and you project on a low dimensional space, it's known that we project Gaussian in low dimensional space, you obtain uniform measures. So that's kind of why the Bargmann Fock model, when taken in high dimension but projected on low dimensional space, is going to be close to monochromatic waves in high dimension when projected on a small dimensional space. Of course, that doesn't mean that the behavior, the macroscopic behavior, will be the same, but I will explain a little bit more why this is the case towards the end of the talk. Okay, so these are the two models at hand. Pick your favorite one. And what are we interested in? So first piece of information we would be interested in is to answer the question, is there an unbounded connected component in X, let's say I'm gonna X smaller than L. So you take all the places where X is smaller than a certain parameter L, and you ask whether there is an unbounded part of the space in this set, okay? So in order to make sense of this question, we usually, as probabilists, introduce a parameter, which is the first L in R, if it exists, such that the probability that there exists an unbounded connected component in X smaller than L is strictly positive, which, by the way, here, in fact, by ergodicity, you could also just ask that it's equal to 1. So it's either equal to 0 or 1. So as soon as it's positive, it's equal to 1. And when you look at this, now the question is, can you compute LC? Or can you estimate LC? So here is a table of what is known and not known. So I'm well aware that I'm going a little bit fast on I'm not going to recall all the history and so on, but again, I want to really focus on explaining a little bit of the key ingredients of the proof. So I'm going to go in a minimalistic way up to the proof. So for random monochromatic waves, so there is going to be 3 cases of interest for us. At least 3 categories of results. So first thing, in dimension 2, it's known that for both random monochromatic waves and Bargmann Fock, it's known that LC is equal to 0. And this is a result. So it really means that if you take X smaller than L with L negative, you will never see an infinite connected component. If you take X larger than epsilon for any positive epsilon, you will see an infinite connected component. And this is a result which is fairly recent, actually, in this level of generality, which is due to Muirhead, Rivera, Vanneuville, and with an appendix by Köhler, Schrinder. This is only one name. And basically, they prove this thing. It's a very cool result, by the way. I recommend reading the paper. And so it proves that LC is always equal to 0. And basically, for almost any kind of reasonable field you would take, it would be equal to 0 in dimension 2. That's the important. The object of this talk would be to prove to you that, in fact, here, LC is smaller than 0. Okay, and this will be the object, this will be the main theorem of this talk. So it's a result by myself, Alejandro Rivera, Hugo Vanneuville. Oh, if you can read what I just did, you are a hero. Alejandro Rodriguez, but you can read it here. This is Vanneuville. This is the same word. And one of the nice byproducts of this result is that by this kind of approximation between Bargmann Fock and random monochromatic waves, you can actually also deduce LC smaller than 0 in high dimension. And this approximation of these 2 fields, the fact that you can approximate both fields, this is a nice observation by Alejandro Rivera. So he chose to put it in a different paper, which I think was an excellent idea. So this is formally almost a corollary, but it really relies on this very nice observation. And here remains maybe one of the coolest questions in the field, is that proving that LC is equal to 0 here, and this was the original conjecture by Peter. Okay, so this is kind of the elephant in the room. I mean, how can we get this property? But this is the only remaining somehow step in this story. Of course, if you are...
May I ask you a question? Is the high dimension effective or
Or
so
I guess you can make it as maybe effective, but I mean, it will be so catastrophic that it's not like it's not 19. It's
okay.
It's not something like I mean, it's really going to be catastrophic, and I guess optimizing the value would be anyway a little bit difficult. So and yeah, I think probably there would be lower bounds on the like possibilities of making the argument work, because you still need, for instance, that your like a two-dimensional slab, you would need sufficient rapid decay of the covariance function of the random waves, which would, I think, not be true in dimension 3 and maybe 4. 4 would be borderline. So clearly, even with the best approximation things you could imagine, you would not manage to go below dimension 4, I think. You really need something different to go to dimension 3 and 4, I think.
In dimension 2, the fact that LC0 is really, as you said, a remarkable thing. It's almost as good as Keston's theorem on percolation. Like, it's very rare that you have an exact number.
Yeah, it's exactly actually based on the same metaphysical reasons, but then the proof, the proof is actually not much harder than what, basically Keston did it for Bernoulli percolation, but let's say in the 10 last years, there was a lot of progress on understanding these sharp threshold phenomena for dependent models. So then it becomes, this was kind of easily extendable to continuum percolation like these Gaussian fields. But
let me ask you a question, just because you're going to leave dimension 2. Well, you're going to use dimension 2, I'm sure. But the fact that it's that in the continuum you have all these models just giving one answer, there isn't an analog of that in the discrete, or am I wrong? Like, is that... No,
in some sense there is an analog. All models that are self-dual at a certain point have their critical point at this level. So basically, this is a general underlying fact which allows you to compute the critical value.
This is much more general.
Sorry.
All right. This is going to be true. It just relies on the symmetry of the field.
Yeah.
So
which is, which kind of says that
much more general structure, and you'll still have it.
Exactly. So any function which is symmetric, any random function which is symmetric in law, if you take the super level lines percolation things in 2D, it will always give you 0.
Very general fact.
Maybe so just what I wanted to say just here to emphasize the very nice aspect of this paper is that as long as you have positive covariances, then the techniques that we developed for other models of dependent percolation models were working very well in some sense. Here, for random monochromatic waves, you don't have this FKG inequality. So they found a very nice way to still use this obvious fact that when you increase the parameter L, the set of X smaller than L is larger and larger. So you still have some kind of monotonicity that way. But to go around the fact that the type of monotonicity that one uses for studying dependent percolation models usually was actually stronger than that. We required more. And so they went around it, found a weaker result, but really found something very cute. And based on concentration of Gaussian measures, it's a very, very nice paper. Okay, so I got carried away a little bit. I'm sorry about that.
Can I ask you
But-
last question on the
Yeah, of
dimensions?
course.
I promise to let you speak after.
As long as you add me this time at the end, that I'm fine. Yes, go ahead.
So tiny question, is it clear in detail what's actually happening? So do you have like as lambda increases the square root of lambda, 1 over square root of lambda chessboard, or there is more to it in dimension 2?
1 over square root lambda.
But I mean, my question is, do you know the size of the components and things like this? Is it well
All the
controlled?
techniques I'm going to describe right now are really techniques about the large scale behavior of these percolation models. It's going to rely very little on the microscopic properties, in particular the size of the small components and things like that. So we have very, very little information on this type of things. It doesn't come from this type of arguments, basically. So yeah, I don't know. So here, I mean, having really like understanding this type of shapes here.
Exactly, yeah, that's my question.
That you don't, for instance, you will not at all distinguish between these two things. Like you will not see the difference. You will only see about whether there is macroscopic connected components or not. These are the type of things that you can control, but not at all the microscopic things. And in general, I mean, the type of math that we do in these percolation fields, I mean, we usually study things that are actually expected to be universal at the end. So universal properties of these models, meaning properties that are shared by whole families of models like that. And here, for instance, the scaling limit of these models should all be the same, but you see that the local limit is quite different. For instance, here, you will see sometimes huge balls of like full occupied, which you don't see in monochromatic waves. You have like constraints that force you to alternate between white and black much more than in the Bargmann Fock. So all these non-universal properties, we will have basically zero control on it. And there you really need to go more to the techniques, more theory, and all these things that, I mean, that you people know much better than I do.
But I mean, they're different. These two models are in different universality classes, right?
No. In terms of microscopic behavior in dimension 2, they are both the universality class of percolation, of Bernoulli percolation.
No, I mean the Bargmann Fock model should be in the, I would guess, in the usual, nearest neighbor model. I mean, it's short range.
The prediction is at the monochromatic waves as well. Yeah.
Beg pardon? But
So
no,
the prediction is at monochromatic waves as well.
I don't agree with that. We can discuss that.
I think that's a common. I mean, at least that seems to be the majority of the community.
Concerning large components, it's H.
I'm talking about a large structure. Yeah.
Yeah. Then they both had criticality. Yeah.
No, but I mean, so Peter, at criticality, there are several universality classes for the possible behaviors, but it does happen that the monochromatic waves, I think, is predicted to be in the same universality class as Bernoulli percolation.
Now, for example, nu, the exponent nu, when you go, those are predicted by Weinrod-Halpern to be quite different from what you get.
Okay, so I mean, let's maybe discuss this later, but that's not what I understood. But I mean, I may be wrong. I think it is predicted that monochromatic waves will have a quasi independence property, basically. But, okay, I mean, I don't know these things so well. I mean, I'm not a specialist of monochromatic waves.
And ask again, I mean, if I have a free field, right? If I take a three-dimensional free field by Marinov and Leibowitz, then they're certainly claiming something different happens. Now, maybe because of the
three dimension would be different. That's I mean, this
that's what I was talking about. Yeah.
Okay. No, I'm talking about 2D right now. I'm talking about 2D. Sorry, that was maybe the misunderstanding.
That's the misunderstanding on my part.
I was talking about 2D. I mean, 3D, we don't even know where the critical point is, and we have very little understanding of of what is happening at the critical point. I mean, sorry. So then maybe that's why we.
But there is.
Yeah, that was a confusion.
Yeah. Okay. Good. Very good. I'm feeling better because I was very confused about. Okay. Very good. So let me go back to the second question that one could be interested in, is to understand if there is an unbounded connected component in actually X equal L. And more interestingly, of course, here, and I'm going to actually allow myself this small simplification, the real interesting case is X equals 0 because you already get the nodal domains. Okay, so is there an unbounded connected component? Sorry. So there again, we are going to make our small table. And why do I put a P here? Okay. So dimension 2, dimension 3, and high dimension. Okay, so here, the answer from our results is going to be yes. So in fact, it's easy to see that if the critical point is smaller than 0, by symmetry, that means that you have an infinite black and an infinite white connected components, and then you can easily see that the boundary of it forms an infinite connected component of X equals 0. So this is not a very big mystery once you prove LC smaller than 0. You could imagine that actually LC is equal to 0 and still you have an infinite connected component. And that's why we went directly for the kill to go directly for LC smaller than 0 in order to be able to easily deduce the other thing. But a priori, you could imagine you didn't need that. Here, it's known, and it's actually a result of Alexander, one of the first results in this area, that there is no infinite connected component for Bargmann Fock. It's actually an adaptation of a classical argument of Bernoulli percolation. It's really not, I mean, it's called Zhang argument. You actually have even other ways to do. So this is quite classical. It is predicted that there is no for random monochromatic waves, but it's an open question. It's a very nice open question. I think it's the biggest open question in 2D that is remaining before getting to really these scaling limits, which seems still out of reach. So really try to understand that there is no infinite connected component of X equals 0 in 2D. And in 3D, because we are expecting from Peter's conjectures and LC is smaller than 0, then you should get an infinite connected component. And that's also, I mean, that would be a byproduct of this conjecture. Okay. So this is what is known.
In your work,
yeah.
How about there's only one component? There's one giant component?
Yeah, so in all these cases, when
LC is less than 0.
When there exists a infinite connected component, one expects, and here I'm going to come back to this maybe later because it's not proved in generality, one expects uniqueness.
Okay, thanks.
And it's very much, I mean, it's going to become, there is a point in the talk where it's very natural to talk about that. So let me postpone this to the right moment. Okay. In fact, you even expect some kind of local uniqueness, but I will come back to this. Okay, so let me sketch the proof. Obviously, in 1 hour, I don't have time to tell you about all the details. And fortunately for all of us, because in particular, they are actually more technical than we were hoping so. We did hope that the proof would be a little bit milder because the ideas are kind of sufficiently nice that you want to be presenting them. But then when you write them down, it becomes a little bit of a mess. So let's stick at the level of just sketching the ideas. And the first step is actually a step which is understood for a very long time. It's a very general step. It's due to Muirhead and Vanneuville. And basically, it says the following. It says one can approximate your field by a finite range field. So one can approximate X restricted to a ball, say, of size R, by a field Y, which would be in fact something depending on R. But I will just remove the R because otherwise I'm going to get completely confused. Of range square root log R. So remember, I'm with Bargmann Fock. Okay, if I would have to work with a more general field, then I will not be able to take square root log R, but I'm going to stick to Bargmann Fock to simplify our discussion. Actually, we get more than that, but we'll stick to that. So by this, I mean that if I look at the probability that, let's say X minus Y restricted to the ball of size R, the probability that it's larger than something tiny, I don't remember, but maybe let's put R squared, something like that. This is like very small. Or let's say standing. I don't remember exactly what is the bound we get, but clearly it's smaller than something like 1 over R, for instance. Okay. And this is not that difficult. Basically, it consists in, defining your field Y as being the field with the same covariance but truncated, and then observing that two fields that are very similar covariances are very close to each other with very good probability. I mean, you can couple them in such a way that they are very close to each other with very good probability. So there is nothing deep behind that, but I mean, it is not trivial to prove. So this is typically a step I'm not going to spend time on, but what I want you to remember from that is that now we are always going to be
Can you just remind what is the range to be square root log R?
Oh, I didn't hear you well. Can you just repeat? Sorry.
What does it mean that the range is square root log R? Does it mean that for
yeah, exactly. So yeah, that's what I was going to say. So what do I mean by range square root log R? That's your question, right? So by this I mean that now we are working with a field that satisfies that if you take two sets A and B, and if they are distant of more than square root log R, then events depending only on A and only on B are just independent.
Thank you.
Okay. Yeah. So now we have this independence. So in particular, when we are going to do some renormalization, if you take two boxes that are sufficiently apart, meaning at distance square root log R, if they have size R, then they are independent of each other. What happens in both things are completely independent, which really simplifies a lot your life. The second step is something I want you to have in mind for all the proof, even though we don't quite use it, but we use something a little bit stronger. I will come back to this, but it's something I really want you to keep in mind, is that in 2D, there is this property called the Rousseau-Simon-Welch property, which tells you that basically, when you take kind of reasonable shapes, the probability that there is a path in X smaller or equal to 0 is bounded away from 0 and 1. So in particular, a specific case, which is very easy, of this Rousseau-Simon-Welch thing, is that if you take a square in 2D and you look at X smaller than 0, smaller or equal to 0, then the probability that you have a path from left to right in this square Well, it's very easy to compute. This probability will be equal to 1/2.
So
Why?
what model are we using here in this?
Yeah, I'm going to get to that. Exactly. So basically for any model, again, to take to go back to what Tom was mentioning, any model for which X is symmetric. Why? Because if you do not have a path of X smaller than 0 in red, then you must have a path of X larger than 0, which is blocking it.
Yeah,
but
thanks.
if the law is symmetric under flipping, because I take a square which is itself, well, actually, sorry, I should also assume pi/2 rotation. But I mean, all our fields are usually radial in this framework. So if you assume furthermore that you have this pi/2 symmetry, then you get the same probability of having the path and not having the path, which means you get probability 1/2. But that has a kind of direct implications that imagine that you take now a slab of height log r. So you take the square, but you add some thickness to it. Okay. Then it's very easy to see that the probability that there is a crossing from left to right is actually going to tend to 1. Why? Because every square root log r, you have probability 1/2 of crossing. So in fact, this is larger than 1 minus 1/2 to the square root log r. So it tells you that crossing a kind of balanced shape, like a square, but with a little bit of thickness, is actually very easy. So that is a first kind of red flag that something is very different in higher dimension than in dimension 2, that the crossing probabilities are very, very close to 1. That is not a sufficient property to kind of guarantee that you are necessarily going to be, in some sense, supercritical, that there will be an infinite connected component. There are models, in particular high dimensional Bernoulli percolation, for which at criticality, there is very good probability of crossing a square, a square box. So here, we are going to have to do better, but underlying our whole story, there is going to be this property that actually having long path in my percolation process is very easy. There are many long paths. So it will not come as a big surprise that the third step, and actually most important step, up to now it was kind of not so difficult, but the most important step is going to be to prove that in fact you can glue this long path. You know that you have easily long path. So what you need is to prove some kind of what I would call quasi-planar. Because here realize that the size, the horizontal sizes are much bigger than the vertical size. So I'm in something that looks quite planar. So I will prove some quasi-planar uniqueness property. And what do I mean by that? I'm going to prove the following theorem. I'm going to sketch a proof, but this is really the key of our theorem, that if you fix an eta positive, then the probability of the following is very close to 1. I'm going to ask that all connected components of y smaller than 0 intersected with 0 R2 times 0. Oh, by the way, let's fix d equals 3. I don't want to be having like d minus 2 everywhere. Let's fix d equals 3. It's the hardest dimension to actually prove the property. So let's focus on this one. So what I do is that I ask that all the connected components in the plane, in the projection, in the plane, sorry, of diameter larger than epsilon r. So I have my plane, my box. Oh, let's say I'm going to try to draw it in 3D. So I have my box. I'm taking all the connected components which are large in the bottom, on the bottom of my box. And what I ask is that all these connected components of diameter at least n eta r, that they are all connected to each other. So you cannot ask that they are all connected just looking at the bottom of the box. This would be actually contradicting the Rousseau-Semmelweis theory. It will tell you that already in the plane somehow you have very good probabilities of connecting. But what you can ask that they are all connected in the actual box. So in 0r square, sorry, this is r square, times 0 log r. So if I'm allowing in some sense to go in the third dimension a little bit, then I manage to connect all these connected components with very good probability. So here, I guess you get something like log r squared at least, or something like that. Something super polynomial for sure.
Before you move away from this page, so I assume step one is not going to assume that the correlations are positive. That seems to be a decay condition. Am I right? And it's step two and three.
Yes, you're right.
Okay. Yeah. So step 2 and 3 where the positivity is absolutely used.
Yeah, step 2 actually don't even really use it if you keep really the square box, because the 1/2 here doesn't depend on positivity of the covariance. And then if you have independence, it's fine. But definitely step 3 will use it in a very, very, very crucial way.
Okay, thanks.
Okay. So let me tell you before I actually focus on this step 3, which I guess you will all agree looks like the hardest part of the talk, because step 2 and step 1 is kind of technical, and step 2 you can definitely believe that it's almost a proof what I did. Okay, it is a proof. So
step 3 again. I didn't catch it. It went a little fast for me.
Yeah, okay. So let me redo just, when you don't explain well, you should just explain bigger. So let's take a big box.
Okay.
R by R. And I'm looking at all the connected components. So I'm for now in the plane. So already in the intersection of the box with the plane. Okay. And I look at all the connected components of size of diameter larger than eta times r, where eta is a parameter I fix. Think 1/1000. Okay. You look at all these connected components, and if you think in a planar fashion, there may be several of these connected components, in fact, a tight number usually, and they don't have any reason to be connected to each other. There may be 1, but there may be 2, 3, 0, like 100. There may be a certain number of such connected components. And the probability that they are all connected is definitely not close to 1. But what I'm saying is that if you allow yourself now, we are thinking of a 3-dimensional field, right? We are only looking at the projection at the intersection with the plane. But now if you allow yourself to go in the third direction, and that you allow a height, say, of log r, then what I claim is that all these connected components are connected by path that use this third direction up to log r. Okay? So I'm saying the probability that all the red clusters are connected together in this slab is very close to 1. Okay?
So you just have to assume that you have clusters of this size on the 2-dimensional block.
Well, if none of them, if none of them are there, then automatically they are all connected to each other. I mean that's the convention I'm using basically. So what I really want to avoid is that there is more than 1. Like there are 2 that are not connected to each other. Trish, do symmetries of the continuum as opposed to working on lattice ever help you? Okay, so in step 3, it's going to help us, but for a reason that maybe for now you don't even see what is going to be one of the key difficulties. And in order to overcome this difficulty, actually, the continuum is going to be very useful.
Yeah, it's a great question because I've always felt this is easier in the continuum. So we're going to watch.
For many reasons, actually, technically it looks harder, but there in our papers, there is at least one key idea, which was one thing that I really enjoyed very much, that there is an idea where we use the continuum in some really crucial fashion. And there are not so many arguments in this literature that was using continuum in a crucial fashion, but here there is really kind of a deformation of the space argument you are going to see at the end, which uses continuum in a crucial fashion. I have zero clue how to do such a thing in a discrete thing. So I think this is a nice feature of the proof. Okay, so just before I go back to the step 3, let me explain step 4, which maybe in another context I would skip by just throwing at you some big word, but maybe I want to tell you a little bit about this. So there is going to be a multi-scale analysis.
Hugo, there's another question on the chat. If you
I didn't see, sorry. I saw, okay, I don't see another question in the chat. So I don't know whether it was asked.
It was an answer. It was a...
Yeah, because there is a brown...
okay, so it's
She's happy with my answer, basically. I mean, I'm paying him, so I'm not sure that him being happy is...
But I'll put 2 thumbs up.
This well. Okay, so step 4 is a multi-scale analysis. So let me briefly sketch it, because it is important to understand how we get actually the random monochromatic waves. So what we are going to do from then is actually construct what we call and what is often called a finite size criteria. So in some sense, we want to be able to measure locally that there is going to be an infinite connected component. So we want to be measuring an event in a finite box, which is so strong somehow, which is suggesting so strongly that everything is well connected, that from this event, you can deduce automatically that you have an infinite connected component in the full space. So there is some kind of a bootstrap operation that you go from finite volume to infinite volume. So typically what we are going to say is the following. We are going to say that y smaller than L even is 0 good at scale R if you have the following. If there exists a macroscopic, if there exists a connected component of y smaller than L intersected with the box of diameter larger than eta R, where eta, again, think of 1/1000, for instance. So exactly this is answering the concern of Tom that, you want to have a large connected component. So indeed, you want this. Second item you are going to ask is you are going to ask your local uniqueness. So the quasi-planar uniqueness. So any large connected component is connected when you use this third dimension, but here maybe you want it for size 2R instead of R. Okay, so a little bit bigger, like any 2 guys in a bigger box, or maybe 3R to be safe. 3R. Any guy in the box of size 3R are connected. Okay. And the last thing, and here allow me to cheat a little bit. The last thing is that you have this approximation between X and Y, because you cannot ask that X and Y are close everywhere. Here I was very careful to say that X and Y are close in the ball of size R. So I'm going to ask the same thing. So X and Y in the ball of size. Oh, what happened? Panic. Okay. Was my turn? Was my time already done? Okay. So 3R. This is smaller than some tiny thing. Okay. And what I claim is that here, the probability, I mean, I can tune basically the parameters. So I have a parameter L here. I have a parameter eta and a parameter epsilon. Okay. And I can choose R after choosing all these parameters. And what I claim is that there is a way to choose L, R, eta, and epsilon in such a way that L is like minus 1 over R to the, let's say, 3/2 or something like that. I can choose eta to be 1 over 1000, say. And I can choose epsilon to be 1 over 2R to the 3/2. In such a way that the probability of being 0 good is larger than, say, 99%. I claim that, and this is not very difficult to do, basically, out of the 3 first steps, to say there exists R large enough such that I have this property. So this property is really telling me I can approximate very well. This is step 1. There exists a big connected component. This is in some sense step 2. It's actually even a little bit weaker than step 2. And I have the quasi-planar property. This is quasi-uniqueness property. This is really step 3. From there, and notice this is something that depends only on the box of size, basically 3R. From there, I claim that if I have this, then automatically I have an infinite connected component. And the reason for that is that I was careful to say I'm 0 good. So then I can define recursively the fact to be n plus 1 good at scale, I don't know, c to the n r by asking the following. I'm going to be n plus 1 good. So now I take a box of size c to the size c to the power n plus 1 r. And I'm going to say I'm n plus 1 good if all but at most like 2 boxes or maybe 10 boxes are n bad. So I want all that, basically all the boxes of size c to the nr. So I pave my box of size c to the n plus 1 r into c square or c to the d boxes of size just the scale below. And I want that all but 2 of these boxes are n good. And what I claim is that this probability of being n good is actually getting to 1 very fast. There is an easy way to see that it gets to 1 very fast. It's a very standard multi-scale analysis. Diving into it will take me way too much time. But what I want to be advertising is that then, if the probability of being n good at scale c to the nr, so I need to choose c a little bit carefully, but let's not enter into this. If this tends to 1 as n tends to infinity, then I will know that there is an infinite connected component for the following reason. Let's take, to be certain that I'm making the thing big enough. So let's make a very simple thing where I cut it in 3 only. Then I have something like that. And let's say I'm looking at the 3rd scale. So I know that this big scale, this big box is 3 good, or 2 good, sorry. If it's 2 good, that means that there is all but, okay, let's say maybe 1 box that is bad. In fact, it's more than 1, but for my drawing with 3 things here, I need only 1. So here there is at least, at most 1 box, which is 1 bad. Let's say it's the center one. That means that all these boxes are 1 good. So in particular, this box here is one good. So that means that there is at most one box in it, which is 0 bad, etc., etc. So now what happens is that imagine that here, all the macroscopic clusters are actually connected. Remember the drawing here. So all the macroscopic clusters are connected in the third dimension. So because each box has at least one such macroscopic guy, and because I ask the log quasi-planar uniqueness in the box of size 3R, then that guarantees that the macroscopic witnesses, if you want, in each one of my boxes, they must be connected to each other by a path in the third direction. And this is going to create naturally a connection between all the green clusters, all the witnesses at level 0. And because you have very few bad boxes, these bad boxes will not manage to prevent the existence of connections between an infinite number of such witnesses. So this is the core of this multiscale analysis. I'm cheating in several small places, but it's really basically the moral of it. Now, why did I spend some time doing that? Because the important thing is that the starting estimate of being 0 good, the thing depends only on the box of size R that you choose at the beginning. And notice that it's also a property that depends only on basically a two-dimensional box. So if you go back to what I said at the beginning, which is that if I look at a small dimensional subspace of RD, and that on this subspace, I am able to compare Bargmann Fock to random monochromatic waves. If I have a finite size criterion for Bargmann Fock, I will get a finite size criterion for random monochromatic waves. So then from there, you can run the same multi-scale analysis and get your result in high dimension for random waves. But really the core of the thing is to get this finite size criterion in Bargmann Fock. Okay? Okay, and the fact, and in some sense, you only need to work at y equals 0, at y smaller than 0, because these are to this small threshold, the fact that you're allowed to move a little bit down is actually kind of trivial out of stability, that if you change just a little bit your field in a box of size R, you basically don't change anything. And so you just use this, and then you do your multi-scale analysis to get. Okay, let me finish. So where am I now?
Hugo?
Yes, yes.
Just a clarification. The quasi-planar uniqueness, is it in the two-dimensional, or is it again using the third dimension in a log R?
Yeah, the quasi-planar is really in a log R thing. Yes, yes.
Okay.
By the way, I mean, this log R is a constant, right? I mean, since you fix R, the log R will be fixed. So actually you get even something stronger, right? Which is that you get percolation in a slab of size log R at the end, in a two-dimensional slab of size log R. This is maybe something that at first sight is not that obvious. So you get percolation in actually basically a two-dimensional space, but with some thickness. Yeah. So where I definitely cheated, what happened here? Yeah. Is that this here is actually introducing I mean, what you are going to use to do your multi-scale analysis is that you want things to be basically independent, which is very good because Y has a small range, log R. So in particular here, if I take two boxes, let's say this one and this one, because they are not adjacent, they are at distance at least log R of each other, so they are completely independent. But notice that this property here, when you compare to X, then you actually lose completely independence. So you need to modify a little bit this argument. It's not that difficult to modify it, and it runs very smoothly. But I just wanted that you don't catch me on this one. It was a voluntarily slight simplification of the multiscale analysis to give you at least the juice of it. But I'm very well aware that if you do the thing like that, here you lose independence because of this X. So that's
can I ask you a question?
Yes, of course. Yeah.
Maybe it's obvious, maybe something you already said and I just wasn't paying attention to it yet. But what sets the log R height?
Sorry, what
is it that sets the log R height? I mean, why is
the log R height here is set because I have a very small, very little imagination for functions. Yeah, for Bargmann Fock, you could actually do anything which is square root log R. I mean log R to a power 1/2 plus epsilon.
It's not sharp. It's just convenient.
Yeah, it's not sharp at all. Basically, you need that boxes will typically be independent if they are at this. I mean, almost independent in the original X, and because of the very rapid decay of covariances here. You see that if you take two boxes which are at distance log R to the 1/2 plus epsilon, then they will basically be independent already. That's basically, so anything with log R to the power 1/2 plus epsilon would work. Actually, in our paper, we do a much broader class of covariances. So then you are not even allowed to use log R. You need to go to distance R to some power. But just here, yeah, it was lack of imagination. I thought log R is bigger than square root log R, and it's smaller than R to the epsilon, so it will scare people much less.
Sorry, your main theorem in dimension 3 uses the positivity of the covariance and any decay faster than any power.
Yeah, I mean, you don't need faster than any power.
On the dimension.
You basically need fast enough that you have. If you take two boxes at distance like R of each other, they should be independent. Okay. So I think we at the end we kind of maybe didn't optimize and we get something like a large power, but morally speaking, you want that two boxes at distance R of each other of size R are independent. This should be.
You certainly don't need exponential.
Yeah. Certainly exponential. Fine. Okay, so let me now step back and try to do this step 3 or give you an idea of step 3. And first, I'm going to cheat. I'm going to tell you where I cheat. I'm not going to do this nasty game of making you believe you have a full proof and then asking to point where the mistake is. So I'm going to tell you a little bit the philosophy and then how you need to modify. So, as I said, this is going to be the main novelty in some sense of the paper. And let's start by a parenthesis. So a parenthesis. I'm well aware that I'm reaching the end. I think I have no grasp on people in IAS, so you can leave the room without me being annoyed, and I'm going to still take the 10 to 15 minutes I need to present this, because if I rush, then nobody will understand anything. So I feel like it would be a little bit of a loss. So I need, 10 minutes maybe to finish, and I know I'm over time. I apologize for that. Okay, so a parenthesis on crossing estimates. So on this Rousseau-Seymour-Welch. So basically the Rousseau-Seymour-Welch thing is saying, another way of putting it, is that if there exists a constant C, such that whatever the set A and B, included in 0 R squared times 0, connected, and of radius at least eta R. So I take a box of size R and I take two sets, A and B. Let me draw them in green. So for any eta, there exists a C such that whatever the R, whatever the A, and whatever the B, the probability that they are connected, it's larger than constant. this is roughly what Rousseau-Seymour wedge says, or at least it's a very strong form of Rousseau-Seymour wedge, and it's a very useful form. Well, let me tell you that recently we did make a big improvement actually from our point of view, but with Johan Mandurescu and Vincent Tassion, we proved the following thing. So there exists a C, same thing, such that for any set blah blah. But what we proved, and in a fairly large generality, is that not only do you connect A and B, but you actually can connect them with in polynomially many points. So there is polynomially like R to the C points in B that are connected to R to the C point in A. Okay, so it's kind of an improvement. And by the way, it's a kind of funny story because we use a comparison to a branching process, to a Galton-Watson process. And this was, I mean, to our opinion, one of the first time where you could build up a coupling between a critical percolation process and a Galton-Watson tree. Usually you do that in supercritical or subcritical in some kind of nice way, but I mean, subcritical, no, but I mean supercritical or subcritical for the dual. But in critical, it was kind of something that, we never saw before. So there is this nice argument, and this nice argument has, can be the root of a first attempt, basically, to proving the local uniqueness, which is going to be the following. So let's take our slab. And let's remember that it has size log r, but that at every square root log r, you are basically independent, okay? And what I'm gonna do is I'm gonna imagine that I know A and B. These are my two, these are two macroscopic clusters, but in on the bottom of the strip. And what I'm gonna do is I'm gonna take the slice of my box, and I'm gonna just look at the lift of A and B, let's call them A prime and B prime, above my A and B, okay? So they are just the lift on my new layer. And what I know from this theorem, which you can actually adapt to Bargmann Fock, you know that with positive probability, you can connect many points, let me put them in yellow, many points of B to many points, many points of B prime to many points of A prime, okay? So this occurs only with probability C, but what you can do is you can start from the top of your strip, look at really the top of the strip, look at the projection A prime and B prime on this thing and try to check whether that works. If it works very well, you found your place. If it doesn't, you can go down by square root log n and try at this new place because it's completely independent of what you saw before. You try, if it works, very good, you found the layer. If it doesn't, you go down. And every time you are going to go down, you are going to have square root log n tries. So there is with fairly good probability, 1 minus c to the square root log n, you are going to find this level where you connect in many places. But now, imagine for a second you would be in Bernoulli percolation. If you are in Bernoulli percolation, what you see is that it would be sufficient in order to connect A to B. It would be sufficient that one of the vertical tube that is vertical path that is connecting A prime to, one of these yellow points to its projection on the plane, it would be sufficient that one of these guys would be made only of open edges, that you would have a connection that this path is in your percolation process. But what is the probability of this? Well, it's basically constant to the square root log n, log r. This is roughly the cost of having a full line open in Bernoulli percolation. But how many tries do you have? You have r to the c yellow points. So if for each one of them you have a probability c to the square root log r of connecting, then with very good probability, one of these points is going to be connected to the bottom. And same thing on the right. And that's how you would get a connection between A and B. But the problem here, and this is the big problem with Bargmann Fock and random monochromatic waves, is that you will have noticed maybe, or if you didn't, then I'm going to tell you now, that the two covariance functions here are analytic. And that automatically gives you that the fields themselves are analytic. If they are analytic, you see that you are basically the farthest away from a model where you are allowed to condition on something and do whatever you want in the remaining sets. Why? Because if you condition on anything which is big enough, it's going to actually determine your whole field. So you don't have a property that probabilists refer to as finite energy property. You don't have that. And this is the key problem in all of this. So let's be very careful not to use our standard intuition. There is no finite energy. So this argument that is consisting on taking a fiber, if you want, and opening it doesn't work. Yet, this is still the underlying idea of the proof, but what we are going to have to do is to prove that somehow when I condition on A and B, when I condition on all the bottom face, and I look at the big clusters, what I need to prove is that in this big cluster, there are many points that still have good probability of being connected to the top. Because this is going to be exactly, instead of opening brutally one fiber, I'm going to use these properties that the conditional probability of being connected to the top is still good, and I can then play with this argument and conclude. So what I need basically to prove to you is to try to convince you that it's very rare that you have a long cluster that doesn't go up a lot. Basically, I want to be saying that whatever flat large cluster I have, it is naturally connected to the top, to distance log r to the top. If you have that, trust me that you can then play the game of proving that if you only condition on the bottom thing, then there are many points that have good conditional probability of being connected to the top. So what I really need to prove is something that I'm going to summarize in what I will call which would be actually one of the main novelties of the paper. So it's going to be the following theorem, which is that for any eta positive, there exists a constant, let's call it epsilon, such that the probability that all connected components of y smaller than 0 intersected with 0r squared times 0 of diameter larger than eta r, they are necessarily connected to the top, so let's say to 0r squared times log r. So this probability is almost 1. It's larger than 1. Let's say again, it's larger than 1 minus 1 over r or something like that. Okay, so I need to convince you that all connected components, the large connected components on the plane, are naturally connected to distance log r. Okay.
What is epsilon?
This is, yeah.
What is epsilon?
Where is epsilon? That's a very good question. There is no epsilon anymore because actually you can put here, because here you can put r to the epsilon, in fact, even. You can be connected much higher than log r. Sorry about this. I wanted to simplify and got caught. Very good. So, and let me finish by that. It's going to be my toy problem related to this. It's the wiggling pizza slice problem. Please don't cut me on this one. So I'm going to prove to you, I'm going to convince you at least, that the probability that 0 is connected. So let's say this is a slice of pizza. It's size R and R. It has height log R, but in fact, you could even put R to the epsilon. And I'm going to look at the probability that 0 is connected at the bottom to the right of to the exterior of my pizza, but it is not connected to the top of my pizza. Okay? So I want to convince you that this probability is very small. And I'm going to do this like that. So let's imagine you are looking on the edge. So you see this, right? Let's call this event A, by the way. Sorry, let's call it A. So if you look at your pizza on the side, you see R times log R. And what I'm going to do is I'm going to ask the same event, but for a wiggled, like a pizza that I deform vertically by a dig path. So I take a dig path where, sorry, I do something like I go up by at least log R or 2 log R. So here I go up or down by 2 log R, and I do it every R to the 1 minus epsilon. Okay? So I do kind of very slowly varying pizza. So it's not a flat slice of pizza anymore. It's moving a little bit like that. And I choose my dig path D, which is telling me how I go up and down. It's kind of just encoding the wiggling of my pizza. Okay? And I defined, exactly like I defined A here, I defined AD for the corresponding event here, meaning that on the bottom of my slice of pizza, there will be a path from left to right, but there is no path from this cluster to the top, from the red cluster to the top. Okay? And here is the observation. So let's call this AD. I don't want to be changing pictures, so let me try to finish here. So here are a few observations. So there are 2 to the R to the 1 minus epsilon, 2 to the R to the epsilon events, AD, because for every dig path, I have an event. And so every R to the 1 minus epsilon, I'm choosing to go up by 2 log R or down by 2 log R. So that's the first observation. The second observation is that all the AD are disjoint. Why? Because notice that, for instance, if I compare the slice like that to the slice like that, to the wiggle slice, already this part here is connecting 0 to the top of my slice. So it's already telling you are not in A. And in fact, because you choose these dig paths, except if the 2 dig paths are exactly equal, as soon as they diverge, one path is going to force basically a connection to the top for the other guy. So all these events are disjoint. So now you start to see where I'm heading, because, or maybe you don't because I'm very bad pedagogically, but the third property is that you make this wiggling, but it's a very soft wiggling, right? You go up by log R, but you still go by R to the 1 minus epsilon that direction. So now what is going to happen is by using the fact that you are in a smooth field, you can basically remap the thing to the original model, but for us, I mean, so on the original pizza, but just changing a little bit the covariance of your field. But because the deformation is very close to identity, in fact, the covariance is going to be extremely close to the original covariance. And you can prove by Cameron-Martin type arguments, you can prove that the events have similar probability. So they are disjoint, but they are almost similar probabilities. So then you see what is going to happen, that 2 to the R to the epsilon probability of A is roughly like sum of the probability of AD. And this is because these events are disjoint, smaller or equal to 1. and that gives you that the probability of A is very small in the first place. So it's not quite for the event that we were looking for, because here it's in a slice and it's starting from a point, but you can easily extract basically what you want in the general framework from this toy problem. So there is this very nice deformation. We were inspired by really continuous fields and like two-dimensional fields with continuous symmetries to try to use this kind of smooth deformation of your field to prove that the event that you are looking at is too constraining and has too small probability. So it's really inspired by Mervyn Wagner, basically. And this is a nice property. And it's really, sorry, yeah?
This is where the discrete model fails?
Exactly. If you do a discrete model and you try to do that, you have basically no easy way before proving that there is a scaling limit with sufficient symmetries. You have no ways to deform your first thing into the second. Like you imagine you have ZT intersected with this wiggling pizza. Well, how do you relate percolation on this to percolation on the actual like non-wiggling pizza? I have no clue how to do. Here there is a natural deformation, a natural map. It allows you just to rewrite the thing on the original model with a different covariance, but the covariance is very small from very close to the original one. So you can basically relate the two models, but it's really a symmetry of this continuum model that doesn't exist in the discrete. Sorry. So this is basically the end of my talk. I wanted to finish on that because this is one of the main novelties. And I think that this has more probably potential application than just this theorem. It's possible that this is one of the key things that we could try to use to get the three-dimensional random waves question. So the original question of Peter. Well, thank you very much for your attention. Sorry if it was maybe not that clear, but I tried to give you at least a hint of what I was doing. Thank you.
Are there any questions from any side of the? Yeah, Jonathan.
Just to understand that last point a little better. Yeah. I mean, if I have this lattice and I have, a small height perturbation above a two-dimensional plane, right? So I have this kind of discrete version of your pizza, right? In a way, I mean, this up and down, right? I don't understand why, if I just contract back to the nearest point as I go across, I mean, I still have Gaussian random variables. There's nothing that keeps me from doing a change of measure like Cameron-Martin on that correction of lattice variables, right? I mean, so I guess, you see what I'm asking? I mean, there's still.
So if you are with a Gaussian field, maybe indeed, if you have a natural mapping, which is preserving the graph structure, which will not be that clear if you deform the thing, because your connection, right, in discrete, your connections are still ruled by actual nearest neighbors, right? So if you can find a copy, and then that would work. What I had in mind is more natural discrete models in some sense. In the sense, I mean, this Gaussian discrete models would be actually quite close to the continuum one. So maybe there you could save the argument, but I was more thinking Bernoulli percolation or things like that, where there, like, I really have no clue how I would do this deformation.
Okay. Yeah, no, I understand. Thank you.
Yeah.
Sorry for all the questions. Heuristically, I have trouble to understand the known bound that you do between X and Y. The Y is the finite bounded thing, because all the statement that you said on Y, it's not clear how it should imply anything on X by just known bound. Or what is this known bound?
So here you mean you don't see how. So the reason why you want to get to finite range is because you are going to, in particular, in
I understand why I want to get to finite range. I just don't see how how giving a norm bound between the two fields give me such a fine detail, like tracking down.
Because basically what is going to happen is that imagine you prove, so basically what you are going to prove is that something happens for y smaller than -2 epsilon, sorry, and you are going to prove that x minus y in norm bound, so in supremum, is smaller than epsilon. And you are only interested in things that, like, I mean, this is going to tell you automatically that imagine there is an infinite connected component in this.
Oh, okay.
And imagine that x minus y is smaller than epsilon, then it automatically gives you an infinite connected component in x smaller than minus epsilon. So it's nothing deeper than that.
Thank you.
Yeah. But of course, what is true is that you cannot compare x and y on the full space. So what is going to happen is that in your multiscale analysis, you are going to prove that the places you use to construct the infinite connected components are actually also places, I mean, you can intersect that with places where you actually control the norm between x and y. And if you do this sufficiently well, you will manage that in the intersection, I mean, to prove that in the intersection of these two sets, you still find an infinite connected component. So you need to be careful in some sense to both control the existence of large connected components and the comparison between x and y on the same places to be able to really, because here you can, in this intersected with A, and if you can prove that this is true on A, then you get still an infinite connected component. So A will not be the full space. You cannot control the infinite norm on the full space. It's too big. But you control it in the places where you build your infinite connected component.
Thank you.
I believe there is a question in chat. I didn't completely see it, but you probably do.
Are you aware of any work where percolation theory is used in deep learning, if there is any? That's a good question. I'm pretty sure that it can be used, but I really here I would clearly overextend by telling you something on that. I really don't know, didn't follow the application of percolation to deep learning, so I cannot tell you anything smart there.